All right, I'm happy to introduce Evanthia, with a long career of doing different geometric things, and she got her degree with DTV, and then worked at IBM for some number of years, and she's been for a while now in Switzerland, and I guess I will skip the long prepared speech and let her speak.
Okay, thanks. Thanks very much, Boris. Nice to be here. So what I talk about Voronoi-like graphs and applications. So this is part of this topic joint work with my former PhD student, Collier Uninder, and parts are newer work of mine.
You have to switch focus to that thing.
Click on
That arrow, no?
Right. So Voronoi diagrams, I guess everybody, we all here in this room know about Voronoi diagrams. Here you see the Voronoi diagram of points in Euclidean plane. So Voronoi diagrams are a versatile geometric partitioning structure. Focus will be in dystopian 2D. And of course, we can define Voronoi diagrams for different sites and different metrics. So we also all are familiar with the dual Delaunay triangulation of the Voronoi diagram, which you see here in red. So yes, I don't need to explain anything on what is a Delaunay triangulation or a Voronoi diagram in today's videos. So yes, so you have a set of sites which are points, and the Voronoi region of the site P is the locus of points closer to P than to any other site. So every cell here is closer to one site than to any other. And the Delaunay and the dual graph of the Voronoi diagram is what you see in red here, which is the non-Delaunay triangulation. So yeah, the Delaunay triangulation of definition is if you take any triangle in the triangulation and you take the circle defined by the 3 points in the triangle, it's empty of other points. But you can also define it as a dual of the so we can define Voronoi diagrams for different sites and different metrics, not only for points in the Euclidean plane. And here you see a Voronoi diagram of segments. There are well-known differences with points. Like the Voronoi regions are no longer, they are not convex. Bisectors are not straight lines. More importantly, there can be multiple adjacencies between the Voronoi region of the segment 2 with the Voronoi region of segment 3. And same kind of problems, same kind of issues you have with the Voronoi diagram of circles. You see the same things here. You can have multiple adjacencies between the Voronoi cells of 2 circles, like this one and this one. So you get similar issues. Now, these differences are sometimes forgotten. So classic variants of Voronoi diagrams of line segments, polygons, disks have received much less attention in computational geometry. For example, higher order and farthest Voronoi diagrams of segments have been ignored until relatively recently. It was only in 06 that Orenhammer, Drisday, and Tracer look at the farthest Voronoi diagram of segments. It will show some standard differences that we have. Then we looked at the order K, and even for abstract Voronoi diagrams, the order K variant was only defined in 2015. Now, higher order Voronoi diagrams of polygons still have not been considered. Only the farthest polygon Voronoi diagram has been considered so far. Another problem, updating a segment Voronoi diagram in a linear time after deletion of one side. It's still not resolved the problem. We have given an expected linear time algorithm to do that, which I will review in this. So let me give this example of the farthest segment Voronoi diagram to see the differences with the respective case of points. So here we have a bunch of segments. Here in red, you see the farthest Voronoi diagram. For anybody not very familiar, farthest Voronoi diagram reflects farthest information. So the Voronoi region of the site is the lots of points farthest away from that site. So it has some properties surprisingly different from points, like it's not related to the convex star. For example, this long segment S2, which is definitely part of the convex star, it does not have a Voronoi region in the farthest diagram. On the contrary, this little segment S5, which has nothing to do with the convex star, has in fact two disconnected faces, two different regions. And in fact, a single segment may disconnect may have omega and disconnected faces in this type. Nevertheless, it's a tree structure. That's a tree structure with disconnected regions. It has linear size, whereas the number of segments, and can be constructed in a model. So similarly for order K Voronoi regions, a single order K Voronoi region may disconnect into omega n disjoint faces. Nevertheless, the bounds remain the same as with points. So it seems disconnected regions become a theme when you are dealing with non-point Voronoi. Okay. So also we all know that there is a powerful unifying framework, unifying Voronoi diagrams under different sites and metrics. So there is a general framework connecting Voronoi diagrams and arrangements of hypersurfaces in a space one dimension higher. The well-known powerful framework of Admissible and Seidel. The advantage of this is that the results on envelopes of hypersurfaces directly apply to Voronoi diagrams. But still, there can be differences between arrangements of general surfaces versus arrangements of planes, which recently nicely explained in example. For example, for Kaplan, and when they are in the plane, another unifying framework comes from abstract Voronoi diagrams defined by time. So abstract Voronoi diagrams are defined on bisecting curves that satisfy some simple properties rather than sites and distances. And they offer a unifying view to various complete Voronoi diagrams in the field. So let me view the model of abstract Voronoi diagrams. We have a set of abstract sites S and an underlying bisector system. You see here, so bisectors are simply curves in the plane. Each bisector partitions the plane into two open domains. The dominance region, here is the dominance region of P, and the dominance region of Q. And then a Voronoi region for a site P is the common intersection of the dominance regions of all dominance regions for site P. Now the classic model for abstract Voronoi diagrams, we consider some more restrictions to the bisector system. So we have the so-called admissible bisector system, where bisectors are simple unbounded curves. They intersect transversally a finite number of times. And for every subset of sites, Voronoi regions are non-active and connected, and Voronoi regions cover the plane. So when all these axioms are satisfied, we call the bisector system admissible, and that's the standard AVD. Recently, there have been generalizations of this, but that's the standard standard. So the Voronoi region of a site P is the common intersection of all the dominance regions for P. And the Voronoi diagram is we collect the boundaries of all Voronoi regions, we get a graph, which is the Voronoi diagram for this set of sets. So this is the Voronoi region. So some examples of concrete diagrams that fall under the AUD model, like point size and convex distance metric, line segments drawing convex polygons of constant size, linear T metric, additively weighted points, power diagrams with non-enclosing circles, etc. So to address such cases simultaneously, we can work directly with the AUD. Okay, but point sites are not very representative of the ADD model. Of course, they belong in the ADD model, but segments are, and let's see why. Let's see why points are not exactly representative of such Voronoi. So point bisectors are lines. So lines, they intersect once unless they are parallel. Segment bisectors or circle bisectors are not even pseudolines. They are simple pairs of constant complexity, but they are not pseudolines. And when we have segment bisectors that are related, meaning bisectors involving three different sites, so the bisectors share one common site, the bisectors can intersect twice. They intersect at most twice. And that's a great difference from lines. And the same holds for abstract bisectors. They can intersect at most twice. So you see here three related bisectors involving the sites R, P, and Q. They can intersect twice. And two intersections versus one make a difference in properties, in proof techniques. In general, the proofs for ADDs of segments apply to points, but not vice versa. So here is the overview of this talk. So I'll talk about site deletion, the problem of site deletion for points versus segments, disks, and ADDs. Then I'll define Voronoi-like structures, which are just graphs on a bisector arrangement. The site deletion problem actually motivated this definition of the Voronoi-like structures. I'll use the Voronoi-like graphs to extend the Delaunay's theorem from points to abstract Voronoi diagrams. And then I'll address the site deletion in expected linear time by some very simple incremental construction. And update the constraint Delaunay triangulation in expected linear time after a new segment insertion. And if I have time, I'll talk about an alternative to backwards analysis applicable to order dependent structures, because order dependent structures is what appears in this incremental construction. Okay, so let me start with the site deletion problem. So let me first talk about some linear time Voronoi algorithms. Here you see points in convex position. So the Voronoi, and you see the Voronoi diagram of points in convex position. It is a tree diagram, and it's well known that it can be computed in linear time by the algorithm of Agarwal-Gilbert Arc-insertion. And there is a much simpler randomized technique by Chu, which is also very well known, that we can compute Voronoi diagram of points in convex position. And this problem is related to site deletion in a point Voronoi diagram, computing the farthest point Voronoi diagram given the convex skull, and also some order k+1 subdivision within an order k region. And this technique, the technique of Agarwal-Gilbert Arc-insertion, has been extended to some restricted versions of abstract Voronoi diagrams, and it is like the so-called Hamiltonian abstract Voronoi diagram, where we have a curve that passes through one Voronoi region only once, and bisectors can intersect the domain of the computation only once. So here is ideation. We have a Voronoi diagram. We have a set of sites S, and we want to delete the region of one site S. We want to delete this green region and update the diagram. So to do that, to delete S and update the diagram, we need to compute this red tree here, this red diagram, which is the Voronoi diagram of everything else outside the green region, truncated within it. So this diagram is a tree, and we want to compute this red tree. And if, in case the sites are not points, this tree might be points. Okay, so for point sites, the deletion, we can compute this red tree in linear time, either by the deterministic way or by this simple randomized algorithm. For non-point sites, the problem becomes considerably more difficult. So we now have a randomized linear time algorithm to do that for abstract Voronoi diagrams. And why it's more difficult? Essentially, it's disconnected Voronoi regions. The problem of disconnected Voronoi regions. So let's see why disconnected Voronoi regions show up. We have, so you see here, one site like this long segment can have multiple faces in this red diagram that we want to do. So this here, this red tree, is a diagram that we need to compute, and there are several faces for this site out here. So these disconnected regions create problems to an incremental construction, and let me show how. So let's say we are computing the Voronoi diagram segments in this shaded domain. Here we have just 3 segments, C3. Now we consider the next segment. We consider this next red segment. So many faces may need to be inserted to update the diagram. So step I may trigger theta I new faces, and whose rotation we don't know it. So here in this example, we have to insert 2 faces, but in general, there can be step I, theta I new faces. So if we are to compute a true Voronoi diagram, then all these faces must be inserted, and therefore it's difficult to avoid so-called complication. So if we have a different insertion order, then we may need to split a region in 2, as here. We have one region, we insert this 4th segment, and we need to split the region in 2. This is not a big problem. The real problem is that theta I faces may need to be inserted instead I, and these faces do not appear in the final diagram, and we don't know what they are. So we need a structure. Maybe we need this structure on the right, which is a Voronoi-like. So we need a Voronoi diagram, but we need the ability to skip faces. So I'll define such Voronoi diagrams. So let me define that. So let's consider an arrangement of bisectors. Let's consider this under a general abstract Voronoi diagram model. So we have an arrangement of bisectors here, truncated within a domain. So the bisectors are simply curves, bounded, closed, they intersect transversely. So I consider a graph, like what you see here, highlighted, a graph on this arrangement, whose the leaves of this graph are on the boundary of B. And let me make the general position assumption that no 3 bisectors on the same side intersect at the same point. So the arrangement vertices have degree 6. So now let me call a vertex V, the vertex V of G, locally Voronoi. If V and its incident edges will be in a neighborhood close to V, they appear in a Voronoi diagram of three sets. So the vertex is just a legal vertex in a diagram of three sets. So we have a graph G defined on this arrangement of bisectors. It's called Voronoi-like. If its vertices other than its leaves are locally Voronoi. So if G is disconnected, consequently leaves must have consistent figures. And its face of G belongs to a site that labels the bisector of so we can say here is a face in our graph. We say belongs in the site P, just because these are the bisectors. So again, we have the graph on this arrangement of bisectors. It's called Voronoi-like. If its vertices other than its leaves are all locally Voronoi vertices, meaning they are legal vertices in a diagram of these sets. So the question is this Voronoi-like graph a Voronoi diagram? For point sets, when the bisectors are lines, yes. On a line arrangement, any Voronoi-like graph is the Voronoi diagram of the involved sites. But this is not clear for a general bisector arrangement. And this is related to Delaunay's theorem, which says that the triangulation is globally Delaunay, even only if it is locally Delaunay. So let's see an example here. So here we have a Voronoi diagram of two segments. Here you see truncated within a domain V. And here you see a Voronoi-like on the same set of sides. This space F, it is missing from the Voronoi. So the difference between this and this is that this space F does not appear. So that's the Voronoi-like graph, and that's the real Voronoi diagram within this domain. So there is the following observation. Let's say we have a Voronoi-like graph G. Let's take any face on this graph G. So let's take a face A. So one of the following must hold. If there is a Voronoi face A prime in the real Voronoi diagram of the same site as this one, which is contained in A. So this is what happens here. A prime is a subset of A. Or this face A is disjoint from any face of the same site in the diagram. And it's covered by Voronoi faces, which are completely missing from this graph. I'll show an example of this because it wouldn't be very clear. Okay. So the corollary of this is that if no Voronoi face is missing from such a graph, then this graph is actually the Voronoi diagram of the sites truncated. That's where this observation is. So another corollary. So a Voronoi-like graph is as close as possible to being a Voronoi diagram, subject to perhaps missing some of its faces. And another, if the bisector system is admissible, so we have a classic abstract Voronoi diagram with connected Voronoi regions. And if B is the entire plane, then any Voronoi graph is the Voronoi diagram. So as long as we are in the entire place and plane, and if we have an admissible bisector system that cover the plane, then any Voronoi graph is the Voronoi diagram of both sides. And okay, so in a way, this extends Delaunay's theorem to abstract Voronoi diagrams. And another corollary is that in an admissible bisector system, any face that does not touch the boundary of the that coincides or contains a real Voronoi region. Therefore, we are interested in Voronoi-like forests. So from now on, I will always assume an admissible bisector system. Like the definition for the Voronoi-like graph is not assume an admissible system. Now I will assume it. And so to remind you, what we have is bisectors are just unbounded simple pairs in the plane. Bisectors intersect transversally, finite number of times. And for every subset of sites, S prime subset of S, Voronoi regions are non-empty and connected, and they cover it. Then we typically assume a large scale for gamma surrounding all bisector intersections. And the Voronoi region of the site is a common intersection among all the dominant regions for the site. So let me define a Voronoi-like cycle. Voronoi-like cycle is something almost like a Voronoi region, the boundary of the Voronoi region. So it's a cycle in the arrangement of bisectors related to the site P and gamma, whose vertices are locally Voronoi of degree P. So here you see such a Voronoi-like cycle. For brevity, let me call it a P cycle, where P is the site in the interior of the cycle. So its vertex of C appears in it's just in a legal Voronoi diagram of the sites. So such a Voronoi-like site. So the site is to be bounded or unbounded. It's unbounded if it accesses gamma. So if it has gamma. So any such Voronoi-like cycle must enclose a Voronoi region. So here in this arrangement, the gray is the Voronoi region of P when we consider these sites. But this red dashed line is a Voronoi-like cycle. Also, there can be many really Voronoi-like cycles. They all enclose this gray Voronoi region. So there can be many different P cycles for the same set of sites. And that's the main difference with points. In a line arrangement, a P cycle always equals a Voronoi region. So no two P cycles can involve the same set of sites, many different points. But in an arrangement of bisectors of segments, circles, or abstract formal diagrams, that's not the case. And we can have many such P cycles, but they all enclose the Voronoi region. Okay, so if we have such a cycle, it implies a Voronoi-like graph, as you see here. So the Voronoi-like graph, the set of sites is the sites that define the cycle. The leaves are the vertices of the cycle, and the non-leaf vertices are all legal Voronoi vertices in a diagram of the sites. So they are all local. That's the Voronoi-like graph of the cycle. And so we have the following result. So the Voronoi-like graph of such a P cycle has the following properties. It exists. The graph was not clear initially. It is unique. It is a tree if C is bounded, and possibly a forest if C is unbounded. And if C is the boundary of a Voronoi region, it can be computed in expected linear time. Otherwise, in expected linear time, we can compute we can compute the Voronoi-like graph of C prime for some possibly other P cycle C prime, which is either equals C or just enclosed with C. So if our cycle is not the boundary of the Voronoi region, we may compute with this algorithm, we may compute the Voronoi-like graph of a cycle enclosed. So uniqueness and part 3 of this theorem is joint work with Koya, but for a different definition of the Voronoi-like which is a special case. So,
Expected.
sorry?
Expected, when you say expected to time, I'm not sure.
It's
Could be
a
any interpretation of expected.
yeah. So it's like a randomized. It's a randomized incremental construction. So the time complexity of the algorithm, it is expected to be. It is not. It is not linear in the best case. So in the worst case, it's not linear, but if we just randomize the order by which we are handling this algorithm, the time complexity is expected to be. Deletion, yes. So this is so side deletion can be considered, although it started with side deletion. This is a case where this theorem applies. So this is just a more general version of the concept we have for subdivision. Yes, that's the space for this graph that is given. So it doesn't, you don't need any extra data structures, you don't need any extra space. It becomes a very simple thing, but the reason it's simple is because what you are computing is not, they are not Voronoi-like, they are almost there. We are computing these graphs, and it turns out it's there. So the existence actually here is shown by construction. So as long as we have such a cycle, which could be the boundary of the Voronoi region or something more general than this, the Voronoi-like graph is a tree structure, it always exists. And it's unique, and we can compute it in linear expression. Okay. So where do we use this? We use it in to derive some simple randomized linear time algorithms for Voronoi trees and forests. And examples are side deletion in abstract Voronoi diagrams, and of course the related concrete versions. The farthest abstract Voronoi diagram, or the K abstract Voronoi diagram, the iterative construction. We have this model. We can update the constraint Delaunay triangulation after a segment constraint insertion. So simplify upon the previous result by subsequent ground. And in general, if we are given a domain D, and inside this domain D, we have a Voronoi diagram, which is a tree, and we know the order of Voronoi faces on the boundary of D, then we can compute this tree under some mild conditions, and that's what we do. So side deletion is actually the motivation for this one. And there may be other applications on disconnected Voronoi regions. Okay, so let me show the site deletion problem. So consider the Voronoi region of a site S, and so here is the Voronoi region of a site S. Let's see be the boundary of this Voronoi region. And we want to compute this red diagram here, the Voronoi diagram of everything else truncated within this Voronoi region. So let's take the Voronoi edges that define the boundary of the region, and let's graphic S be the sequence of Voronoi edges on this boundary. So to compute, so let's see be the boundary of this region. So to compute the Voronoi-like diagram of C incrementally, we need a notion of a diagram for a subset of these edges. So here we have a sprite subset of all these edges. And we need a notion for a diagram for this subset. So we need the Voronoi-like cycle, essentially, that contains a sprite. There are many different ones. It does not matter which one you use. Any of them will work, and there is no need to compute it with Voronoi. So here is the randomized incremental algorithm. It is inspired by simple algorithm of two. We take a random permutation of the arcs on the boundary of the region. In phase one, we delete arcs one by one, recording their neighbors at the time of deletion. In phase two, we insert them back one by one in reverse order. So we construct Voronoi-like graphs in a series of shrinking Voronoi-like cycles. And at the end, we obtain the we use in the middle an Arc-insertion operation. So given a cycle for a site S, given a bisector that intersects the interior of that cycle, the domain of the cycle, with an arc alpha, we insert alpha to C, and we derive the result. So these are the three cases we have. This is the ordinary case that appears also with points. We insert an arc between two other arcs. Here, the insertion of an arc deletes a number of arcs. And here is the interesting case that differentiates from points. That's a split case. So we are inserting this arc alpha. It splits an existing arc in two. And it creates, therefore, it creates this auxiliary arc that does not exist in C. So in this, that's the intermediate Arc-insertion operation. So given the Voronoi-like graph for C, we insert an arc alpha, and we derive we update the Voronoi-like graph of C alpha. So it's all done in standard ways as we do in Voronoi diagrams. So we trace a merge curve through the existing diagram. This was shown correct earlier. And let me illustrate a little bit the phase two with an example. So here we are starting to insert arcs one by one. So here is the first arc. So we consider the entire bisector. Then we insert the next one. We continue inserting arcs. We build the diagram as we go using this Arc-insertion operation. Now, the interesting case is that when we are inserting an arc beta over this arc alpha, we may split it in two, and we create these auxiliary arcs. Okay. So we keep on inserting arcs in the random order. Inserting an arc may split a region in two. Every arc insertion shrinks a domain. Arc insertions create or delete auxiliary arcs. And at the end, we get what we needed. And when we start with the boundary of a Voronoi region, what we compute will have no auxiliary arcs, will be a real Voronoi. So the algorithm is rather simple. What was not so simple was proving the correctness of it and proving also the time complexity, because the intermediate structures are ordered different. So let me give another example with a constraint Delaunay triangulation. So what's the constraint Delaunay triangulation? We have a set of points, two, and a set of segments T. The set of segments are constrained to appear in the Delaunay triangulation of two. So here is the standard incremental construction on a constraint Delaunay triangulation. First, construct the ordinary Delaunay triangulation of the points in Q. You see it here, the ordinary Delaunay triangulation of this point set. And then insert the segment constraints one by one. So here is such a segment constraint. And update the triangulation after each segment insertion. So when we insert a new segment, two cavities are created. So all these triangles intersected by S get deleted. And we need to compute the constraint Delaunay regulation of each cavity. So we need to retriangulate the cavity. Now, a cavity, like what you see, this blue shape here, it's not a simple polygon. We may have multiple vertices that correspond to the same point. But we can retriangulate one cavity in expected linear time. And it becomes much simpler if we go through Voronoi-like. But it's already known, but we can do that. Okay, so the sequence of the cavity vertices define a Voronoi-like cycle. See, this Voronoi-like cycle encloses the Voronoi region on all the cavity vertices, the set of cavity vertices, union S, the segment S. In fact, in this example, the cycle C is exactly the boundary of the Voronoi region of S in this diagram, but in general, this is not necessary. And so what we need to compute the Voronoi-like graph of C, so what we see here. So C can be derived from the cavity vertices in So we can just apply the randomized incremental construction to the arcs of C. However, if we just apply it, we may end up computing a Voronoi-like graph, not the one that we want, but one enclosed in C. So we need to enhance the incremental construction. So when a split arc occurs, we just call choose algorithm and delete it. Delete the created auxiliary arcs in expected linear time. We can do that because we have points and we know how to with the choose algorithm works to delete the point in one Voronoi diagram. So the byproduct of this enhancement is that the Voronoi-like graphs that we compute are order independent. So we can use backwards analysis to establish the time. So, and from backwards analysis, we can show that it's linear expected time despite these occasional deletions calls to choose. All right, so here we can see this incremental construction a little bit. So here we start always with three sites, the two endpoints of the segment, and one random point. So this is the Voronoi-like graph of these 3 points. And then we do the incremental construction, we insert V4, then inserting V5 would split the region of V4 in 2. If here we call the deletion algorithm, we will get rid of one of them, and we will remain with this. And then at the end, we will insert V6, and we will derive what we need. So let me, since I have some time, let me talk about the time analysis. Let me give this technique, this alternative to backwards analysis. So here in this incremental construction, we are creating various Voronoi-like cycles CI, which are order dependent. So if you remember from the beginning, depending by which order we are inserting arcs, we are getting a different cycle, therefore a different diagram. So what step I does, it computes a Voronoi-like graph for the cycle CI, which corresponds to the first I arcs. So the time complexity is proportional to the complexity of the last inserted region plus some additional parameters which I will ignore for now. And we want to show that the expected time complexity of step I is order 1. However, the backwards analysis, which is standard, this area is not applicable. So let's see. So I'll show a different way of doing this that applies to order dependent. So let's say we have a set of objects. So SI is a set of I objects, here arcs, a set of I objects. Let PI be the set of all I factorial permutations on these objects. We can partition PI into groups of I similar permutations each. So we partition into I minus 1 factorial groups of I permutations each. And we do that using this rule. So given one permutation, alpha 1 to alpha I, we define a group of I permutations. By this rule, we take its element here and we append it at the end. So we create this group of I permutations that have alpha j up here. So its alpha j appears in the last position of exactly one permutation. And its permutation to j has the advantage is it has a minimal number of inversions with respect to the initial permutation. So we analyze the time complexity of step I on one entire group instead of one permutation. And the the strategy that we use here is we reduce the time complexity of step I for the entire group to the structural complexity of one Voronoi-like graph derived by the base, by our base permutation, which is order. So this is possible because its arc appears in the last position of exactly one permutation, and its permutation has just a minimal number of inversions. This makes it much simpler to derive get the derivation. So if the structures are order independent, as we usually do in backwards analysis, then the first item is enough. But by combining these two, the technique is applicable to both order dependent and independent structures. Okay. Then what is missing here, the partitioning the permutations in this manner, it's possible. It's possible to partition a block of I factorial permutations into disjoint groups of I permutations each following this specific rule. This was shown by Levenstein, but this was pointed out to us by Stefan. So with that, step I takes all the right time for each group of I permutations. So on average, it takes constant time, and the average is taken over all possible permutations. And since they are all equally likely, we conclude with the result that the expected time complexity is of step I is constant. So here is the method, which is this alternative to backwards analysis. Just consider a group of I permutations for one permutation P derived in this form. Evaluate the time complexity on an entire group. Take the average. If our sequence is order independent, then the arguments are the same as what. All right, so let me conclude. So the Voronoi-like graphs are useful to hold partial Voronoi information. They are as close as possible to being Voronoi diagrams, subject to missing some cases. And we use it to extend the Delaunay's theorem to abstract, to the model of abstract Voronoi diagrams. And the applications are linear time algorithms to compute Voronoi-driven forests. So and these are different forms that we saw. And some open problems. The deterministic linear time technique for tree and forest Voronoi diagrams. So this problem to do in deterministic linear time. So we believe that we can combine Voronoi-like structures with the technique of Algorith, Gibber's such and sort. And some research progress says that it should be affirmative of that we can do. Other applications of Voronoi-like graphs in 2D, when we have disconnected Voronoi regions. And also consider Voronoi-like graphs in 3 or higher regions. So thank you for your attention.